Hello everyone, I'm Long Yuma from the University of Auckland, Computer Science PhD candidate in third year. I would like to thank everyone for attending my GCC 2020 presentation and thank the committee for offering me this opportunity to present what I'm researching. In this speech, I'm going to share with you regarding why I choose this topic and what research progress I have made by now and the state-of-art conclusion. As you can see in the slide, my paper topic is an iris recognition system implementation with error correction capability by reusing Wi-Fi standard LDPC code. In the next 15 minutes, my speech will cover the background. First is background, which includes the advantage of using irises, a brief introduction of LDPC code, and how the above two get correlated. We call biometric channel. And then I'm going to present the proposed architecture. At last, the result and conclusion will be given. So what is the iris? The iris is a round color particle eye and the region between the red and the green circle that surround the black pupil. In any round-shaped irises, there are some textures like snowflakes, which are very unique from person to person. Researchers leverage this distinctiveness to identify who is who. So the merit of the iris, first is the permanent since it was born, and then it's hard to be injured, copied, or faked. And it's non-invasive, which means that not like fingerprint that has to be pressed on a sensor before assessment requirement is accepted. Iris capture only require people to stare at some areas that is embedded with infrared cameras. The most important advantage is that iris has better performance. There are two terms need to be explained before further present. One we call the false acceptance rate, aka FAR, and the other is false rejection rate. They are the matters of the likelihood that the biometric security system will incorrectly accept or reject an access attempt by an authorized user. So, as you can see, these two diagrams shows an FAR and FR comparison among all well-known biometrics. Please notice that the less the better. The x-axis from left to right displays face, irises, palm, and voice. Accordingly, irises are comparatively good. When we decide to use a biometric security system, it should be like the one on the right side. It shows a typical biometric verification system suitable for any biometrics. Importantly, there are two major phases in that system. One that we call the enrollment phase, the other is the prop phase. If we follow the right dots, we can find the procedure will be as follows. In the enrollment phase, a person standing in front of some sensor, like a camera, and his or her biometrics information is captured. Next, the captured sample will be segmented, feature extracted, quality enhanced, and saved as a template or reference in the data storage. In the prop phase, seen as the blue line, the sensor acquires a person who initiates a requirement of access control, and the new samples will be feature extracted and then be sent to matching modules, where the template will also be transferred. So we got two sequences of the iris data, and they are going to be compared under some threshold, and afterward decision will be made. However, no matter it is iris, face, or fingerprint, variation of captured data inevitably exists, just like we cannot take two identical pictures. Adjusting threshold can change the comparison result, but if we decrease threshold, both correct and incorrect requests increase, leading to a fact that security will be challenged. So it is not the perfect solution. Using error correction code to boost the acceptance rate is maybe one option. Since the application of the ECC, or we can say error correction code, has a great influence on the FIR and the FR values of the system, the choice of the code must be done carefully. Recent years using ECC into biometric systems are not quite open, but there are still some related works. So one of the team they used really solid code to enhance the iris recognition system, and the other they use a small matrix LDPC code to enhance the irises. So all the works can be extracted into a channel model, and let's see how it works. So here is the typical communication channel, and it's very simple, but it's quite normal. The left box, the left white box contains raw messages. After channel coding, attach the biparity base P. The bundle of the data go through a noisy channel and then are received by the receiver to decode. Please be noted that the message and its parity bits in the right white box are all contaminated by random noise. Different from this communication channel module, in the biometric channel module, we call encoding enrollment, we call decoding probe, or verification or identification. In such channel, raw messages are influenced by noise, but parity bits are noiseless, so it becomes less complex than a typical communication channel, which means applying error correction code is going to be a valid method to improve accuracy if the adaptation is done properly. Speaking of LDPC, it was proposed in 1962 by Dr. Gallagher. LDPC code actually has been proved that it can achieve error performance close to channel limit, and can result in a higher net channel gain compared with other FAT codes. So generously, and also applied in many protocols, WiMAX, Wi-Fi, 3GPP, 4th generation, and 5th generation. Why we are going to use the LDPC code instead of other ways to boost or enhance the errors recognition system? Well, I already mentioned that it has better performance than the other error correction code, and another one is the subclass of the LDPC code, which is called the QC LDPC code, is hardware friendly, so it's easy to be implemented in some embedded devices. Compared to neural network, we don't need any training since the addresses are very private. So before this issue, the privacy of issue is solved, it's still very useful using LDPC. And of course, the most important is a supplement for current iris recognition system. We don't need to we maybe only need select work for adaptation if we want to change or we want to improve or we want to update the image processing algorithms. So in this slide, we propose our architecture, and it is based on a hybrid FPGA SoC chip, which can embed hardcore processors to execute traditional image processing algorithms. Meanwhile, provide programmable logic, or we can say PL. So we leverage PL to implement the QC LDP code encoder and the decoder, and some other supporting modules. As we can see in this diagram, the highlighted section denoted image processing algorithm running in an ARM core, so including segmentation, localization, feature extraction, and so on. As most of them are programmed using OpenCV library and are out of our research scope, we won't present their details. But it is mentioned that iris images will be precise in these modules, and their output pattern are one-dimension Gabber data. In this slide, the highlighted section is a new one. If you still remember previous slide, the original iris recognition system usually directly compare one-dimension Gabber result or other type of the data result. So in our architecture, a QC LDPC encoder is deployed to generate encoded iris data when enrollment. Then encoded iris data are stored in some external storage. During probe or verification phase, we fetch iris data for several times during different time slots and merge them together using majority voting scheme. Then parity base P0 will be attached to the output of a majority voting X3. The new sequence X3 plus P0 will be fed into QC LDPC decoder, and X1 prime as the output decoder finally are sent to match or decision module for final decision. The result option is match or not match. Speaking of LDPC code selection, because the longer block codes are closer to channel limits, and we got 1,280 bit long for our iris data, and if we use 648 longs, which is the one standard in the IEEE 082.11n, and we need 2 blocks to represent one sequence of iris data. So we already gave up it. And for the longs of the 1944 is because it has more redundancy and it's not efficient. So we choose at last we choose 1296. We can fulfill the whole block by attach 16 base 1 to iris data. In our all experiment, we're going to use 62K pairs of intergroups, and over 70K pairs of intergroups will be used. And the first group will help us to generate true acceptance rate, and the second pairs of intergroup will help us to generate the false acceptance rate. In terms of the experimental result, by changing threshold from 1 Hamming distance to 100% Hamming distance, we draw this relationship between TAR and FAR. So 4 different experiments are conducted. One is just an error recognition system. It's original. And the other 3 are ones with Wi-Fi standard LDPC code, but implemented using different quantization bits. Because we can only use fixed point in the FPGA part, and it helps us to accelerate the whole speed to precise the data. So all the errors data groups are same between different experiments. If we zoom in, the shortest curve is one from 8-bit quantization experiment. So which means that we got 4 in total curves. So generally, 4-bit quantization LDPC implementation and our test seems to outperform others. See, if we look closer to 8 bits, the one we zoom in previously, it truly can boost the true acceptance rate, but we found the lowest false acceptance rate generated by the 8 bits actually is too high. This is caused by extraordinary error correction ability. And if we see the 2-bit quantization, it is only useful within some sections, which are highlighted with the rectangle red box. If you look into the relationship between the acceptance rate and the different threshold, so when the threshold is between 0 to 0.25, 8-bit quantization LDPC decoder implementation provide the best TAR but worst FAR, and 2-bit provide nearly the same FAR as the origin, meanwhile surpass the origin in TAR comparison. When the threshold is between 0 to 0.1, 2-bit solution has better TAR than 4-bit one. And here are some logic uses of different systems implementing 2-bit, 4-bit, 8-bit quantization LDPC codes. It linearly increases as quantization bits increase, so it really makes sense. So the conclusion of our research, one is that we implement more hardware-friendly QC LDP codes into an error recognition system, rather than other works which only conclude simulation or implement small matrix of LDPC code. And secondly, we found a most suitable class of LDPC code in the Wi-Fi protocols and transformed it into an error recognition system. To be specific, the QC LDP code encoder and decoder are implemented onto FPGA part, and the conventional image processing algorithm is executed in an ARM part. And thirdly, open source errors database is adopted. It's called CASIA, and the performance evaluation can be inherited for the future improvement. So in the near future, we're going to looking for more suitable LDPC code for errors. And if partial reconfiguration, which is one of FPGA technique, is considered, adaptively, we can quantize different type of the LDPC codes, and we can choose the most balanced one, which can balance the logic usage and the performance. And the last one, maybe we can try to modify or transplant the image processing algorithms from the traditional ARM core to FPGA, and make even some single FPGA devices can fulfill the error recognition with LDPC enhancement. Okay, that's the end of my presentation. Questions can be published as comments under my YouTube video, and also welcome to be sent to my email. And I would love to talk with you because the time is limited. I cannot say or speak about any of the details of our experiment. It's really interesting, and hopefully we can have a further discussion about my topic. Thank you, everyone. Thank you, everyone.